Okay, hi. Thanks. My name's Jim. I work at both the university and a research lab called SIX in Stockholm. Today is our national holiday in Sweden, so everyone's out shopping in IKEA, eating meatballs and listening to ABBA while I'm over here. Okay, sort of half true, yeah. Okay, so the talk today is going to be about how do we do collaborative software development in a Hadoop-style environment. And many of you are familiar with GitHub, you've worked with GitHub, you use Dropbox to share folders, you create projects in GitHub, you add people to your projects in GitHub, you have isolation between the projects. But we don't really have that in the Hadoop-style environment at the moment. At the moment, you have this sysadministrator, and the sysadmin is like the king, and you have to go to the sysadmin and say, oh, please create a new project, please add these users to it, spin up a cluster for me, and so on. So the sysadministrator is very much in the loop, and the sysadministrator is busy. Now, you may be familiar, you may not be familiar with a number of new security projects in Hadoop. One of them is called Apache Ranger, led by HopsWorks, and Apache Ranger is an attempt to centralize all of the security policies in Hadoop. And one thing they're doing is they're adding Ranger support to the file system. The file system is called the Hadoop file system, HDFS. Now, the recommended best practice for protecting folders that are also protected by Apache Ranger is to recursively change their permissions to be 000. Now, if you're familiar with Unix, that is a very strange thing to do. But basically what's happening is that folder will be protected by Ranger, and many other folders will be protected by HDFS, and it's a little bit confusing, right? So Cloudera have something similar, and you may or may not be familiar with it. It's called Sentry. Again, it's an attempt to centralize all of the security policies for a Hadoop cluster or Hadoop system. So we can see Sentry's in the middle. You enter your policies in here, and they'll get synced up with all of these components. So you can see things like Hive or Impala or HDFS and so on. And this is a hard problem, okay? So this idea comes from enterprise computing. We have this notion of policy enforcement points. They can kind of handle 1,000 ops per second, but our particular name node I'll talk a little bit about today handles 100,000 ops per second on a workload from Spotify. So what's happening here is we have a problem, which is we have our security policies here, and we have the data, the files in HDFS or the tables in Hive, and they're distributed, and we need to maintain the consistency of them. So how do we do that in a distributed system? So this is a difficult problem. The other problem we have is we can see these red boxes around the caches. We can't have our policies here because the name node can't go and ask Sentry, am I allowed to read this file or not? Is this user allowed to read the file or not? They just look locally for the policies. So it's a difficult problem. Now, the reason I'm introducing it is because it's becoming very widespread. I'm just talking particularly about security here, but this actually is the same for the whole stack. Now, before I show the rest of the stack, I'll just show you how we do it in databases. So in databases, we do it differently. So if we have two databases, DB1 and DB2, and we have two users, Alice and Bob, and we'd like to give some privileges for Alice to do some operations on DB1, we can execute the top query here, right? So grant all privileges on DB1 to Alice from any host. And the same we can do for Bob. If we decide to drop the database 2, the privileges that Bob has on DB2, depending on your database, but they'll be implemented as foreign keys. So when you drop the database, the privileges go. So we have the integrity of the metadata guaranteed because we have a database and we're using foreign keys for it. Now this is different to Ranger, it's different to Sentry. How do you do this? Well, you'll end up scanning directories. So when you implement Hive will have to scan the directories to see if the file is still there for the schema. The same goes for policies in Sentry and Ranger. So the main point here is your classical database will guarantee the integrity of your metadata using foreign keys, so the consistency and integrity of the metadata. Whereas at the moment we have now a distributed system. We've got HDFS, YARN, and so on in the middle, and this is classical Hadoop. This is common between all your Hadoop distributions. You have the file system Hadoop, you have a resource manager YARN for managing the CPU and memory in your system, and then you have some users and applications, and then the different distributions like Cloudera will have these specialized metadata services. You'll have Navigator, which is tailing the file systems log, Sentry, which is our security policies, we have Search Engine, Solr, SQL Engine, Hive, and so on. And then we have obviously Spark History Server and MapReduce History Server. And you may notice that Hortonworks have redone the stack for themselves. Okay, so we now have this kind of vendor lock-in thing based around metadata services rather than the core Hadoop. And the thing you'll notice is that we still have to maintain the consistency of all this metadata with the actual data stored in the file system. So there's tons of code, I mean tens or hundreds of thousands of lines of code in these services to handle the kind of edge cases that arrive when maybe a file was deleted from here but you didn't delete it directly from here, and so on. So this is a challenge. If you work in distributed systems, you'll know that maybe people like Google have moved away from eventual consistency models toward things like Spanner because frankly it's easier to program in, and that's what we're going to talk about a bit now. So the reason why Hadoop actually follows that model and it doesn't have a distributed database at the back end is because the core Hadoop, the file system of Hadoop, it stores all of its metadata on the heap of a single Java virtual machine. So this is HDFS, the Hadoop file system. It's the highly available one if you're interested. We've got a standby name node. And then we've got a log of the updates to the name node, which stores the metadata stored on these servers here, journal nodes. So this is a limit. Spotify have a 90 petabyte cluster. We work with Spotify, and this is a 190 gigabyte heap. And they have a couple of people working intensively on this daily to make sure this doesn't go down. So if you even getting up to relatively large heap sizes is a lot of work and overhead. Yarn is pretty similar. You've got, again, a JVM heap. The cluster state is stored on it in something called the resource manager. We don't have the same scalability issues, but we do have problems with how do you want to update it. If you would like to add a new service to Yarn, change how a scheduler works, it's not particularly table or tinker friendly, or it's customizable. So what we've been doing in Stockholm, both at the research lab and at the university, is we've been working on a project for a number of years of how to make the metadata layer in Hadoop distributed. And we call it HOPS, Hadoop Open Platform as a Service. So what we did in HDFS is that we took the metadata that was on the heap of our Java virtual machine and we put it in a distributed database. So this database is not particularly well known. It's open source MySQL cluster, or NDB. It's an in-memory distributed shared nothing database. If a data node crashes, it continues to work because it's replicated, and it'll scale to many tens of terabytes. So there are benchmarks on it for 200 million transactional reads per second, which is even better than the Couchbase guy. We have a quick question. We have no zookeeper here. So we do our leader election. This is distributed shared memory, okay? So distributed shared memory is an abstraction, the same as zookeeper provides an abstraction. So we just use it to implement our leader election algorithm.
My question is, why not use zookeeper for
So zookeeper won't scale to handle this throughput, okay? So when you turn on your phone, most phones are actually using this database at the back end. So we did a benchmark on EC2, and we got with Spotify's workload, and we got about 2.6x the throughput of the normal HDFS node. And that was generating 100,000 operations per second on this, which in turn resulted on roughly 1 million transactions per second on the database. Now zookeeper won't get near that. Okay, it's a lot of the workload in the database is a mixture of primary key operations, and we have something called partition pruned index scans, and we need support for cross-partition transactions. So there's a lot of new SQL features, I should say, that we're exploiting to get that level of performance. So we have no zookeeper here, okay? Yarn, we've done something similar. So with Yarn, what we've done is we've, the scheduler, resource manager, instead of having a single node, we've now actually split it up. So the scheduler does a number of things in Yarn, or the resource manager, I should say. It allocates resources to applications, that's what the scheduler does, but it also handles the communication with the node managers. So we've taken the communication with the node managers and offloaded it to a number of resource trackers, and these are stateless. They can grow and shrink in size, and the resource trackers communicate through distributed shared memory with the scheduler. And this allows us to scale up, but really the scalability isn't maybe the main thing of interest here. The interesting thing is we can add new tables into the database and do cool stuff. So one thing I'll talk about later is quotas. So in Yarn at the moment, there's no notion of a quota that you can say, oh, I'll give this project 100 CPU hours. We do it by adding an extra table here for quotas, and we just listen for events on containers being freed and allocated and update the table correspondingly. Okay, so then so if one of these nodes fails, a new scheduler will be elected again without using Zookeeper. Right, so that's the platform, but I'm going to move on to, I'm not going to go into too much detail on the actual platform. This talk is more about how do we make Hadoop easier to use, and how does this distributed memory help us make Hadoop easier to use. And I'm going to talk a bit about the concept of what we call project-level multi-tenancy. And what you can think of it as is how do we get projects like we have in GitHub into Hadoop? So I'm going to present a problem first. Many of you may be familiar with Databricks and other places where they say, well, spin up a cluster. So this assumption that you spin up a cluster all the time to start doing something new is taken for granted. But in fact, you don't necessarily need to do it. If you could solve this problem, you wouldn't need to spin up a cluster. You could just have a large cluster, and then people could share the use of the resources on it. So the problem is the following. We have a user, Alice. Alice already has access to the NSA dataset, and we'd like to give Alice access to another dataset called user. Now, the problem is that in Hadoop, you only have one identity, a Kerberos identity, and there's no support for what we call dynamic roles or attribute-based access control. So you can't know when you invite Alice to process this data set what other data sets Alice has access to. Alice can copy the data somewhere else, can cross-link with some other data set. These requirements came to us from we did a large European project called Biobank Cloud on medical data. And for them, this was a key requirement. So we spent a lot of time working on this. So the solution we have to this problem is pretty straightforward. If we create a new project, we'll create a new user identity. All right, the new user identity will be project specific. And we're going to use the file system then to enforce access control. So if Alice is a member of the project users, Alice's user identity will be users __ Alice. If Alice tries to run a job here that copies data here, Alice doesn't have privileges to do it because it's a different user, NSA __ Alice, who has privileges to access that. And it's pretty straightforward. The question is, well, now you have multiple user IDs, you're not running Kerberos. Well, no, we're not. So the user identities will actually be metadata in this distributed database at the back end. Now, that's nice. We can isolate users from one another, but we can't share data. Sharing data becomes copying in this model, and that's what we absolutely want to get away from. Sharing data should not be copying of data. So to solve the problem of copying data, or sharing data, I should say, without copying it, we just introduce another abstraction, which is datasets. And all a dataset is a first-class abstraction. Think of it as being a group in your file system. If we want to add the people in the NSA project to give them privileges or for reading or writing from this dataset, we just add them as members to the dataset group, and they do it. Okay, pretty straightforward stuff. So if we put those two things together, then we end up with project-level multi-tenancy. You as a user, you can log in. We have support for two-factor authentication, JDBC, Realm, and LDAP. It's based on a J2E7 web application server, and the application is called HopsWorks. So it kind of looks like the following. Alice will log in, and when Alice comes into the system, she'll pick a project. So she goes into the user project. When Alice now wants to run jobs in the user's project, her jobs will get launched as that user identity on both Yarn, the file system, and also Kafka. We call our file system HopsFS, by the way, and HopsYARN version. They're fully compatible with existing HDFS and Yarn, the same code base, just modified. So when the user Alice changes to another project, the NSA project, then she'll work as that user. And that's how we're enforcing dynamic roles. So we're giving user interface-based access to the cluster. We're not giving command line access right now. Similar enough to Databricks. The mechanisms, how do we implement this? So if you're familiar with Hadoop, you'll be familiar with something called secure impersonation. When you launch a job, our web application server is given privileges to launch jobs as this particular user. And we'll see that for Kafka, we can't do that. So in Kafka, what we're doing is we're creating a certificate per user. So the certificate per user is a little bit, I just do this briefly. If you want to talk to me offline about it, we can do that. It's based on something similar to what Netflix had talked about recently, a bless architecture. It's a way of provisioning certificates for users pretty quickly. So when Alice authenticates on the server, maybe creates a project or adds a project to a user, or removes a project from a user, we're going to then do something with the certificates. We're either going to create a new certificate and put it in the database or remove an existing certificate. The certificates will be signed by a common root CA. We actually have an intermediate CA, but that's besides the point. And that root CA will also sign certificates for the services. So from the big point of view, user logs in here with a single user ID, and then internally within the system, you're authenticating with services using your SSA, your certificate. Right. So what's a project? So a project is just, you can think of it as being an abstraction, right? We have users, we have data sets, and if you drew a line around them and grouped them together, that makes up a project. So the project contains maybe a number of data sets in HDFS, a number of topics in Kafka, and then a number of members. And we also have support for notebooks. So in our case, we'll talk about Apache Zeppelin. The next thing we have that's interesting is that a project has an owner. Now, this came to us as a kind of requirement from Europe have a new General Data Protection Regulation Act for privacy of data that will appear soon, but that was our inspiration behind it. And in fact, it's been a very interesting requirement for us because Spotify, as many of you may know, are moving to Google Compute, and what they've seen is a lot of their data sets, a lot of their pipelines are orphaned. They don't have owners. Right, so if you enforce that from the beginning, that your system has owners for projects and so on, then it is very useful. Question? Okay, the question is, are we cheating with Kafka permissions? And the answer is no. I'll show you in a couple of slides. Okay. So the next point is projects have quotas, and this is something that's unique to us. So your project has a quota in YARN. Do you have? Like I mentioned already, you can give a certain amount of CPU minutes to a project, and the system will account for those and enforce them. Right, so if you're inside a project and you have users, I said already there's a project owner, but the project owner who adds new members to the project can add a person as either a data scientist or an owner. And there's only two roles. We want to keep it simple. So when I talk to people from medicine, they want to have 10 roles. But what we're doing is we're saying that the owner, which is again based on this European General Data Protection Regulation model, is somebody who can import and export data from the system, manage membership, add people to the project, remove them, share data sets and topics in Kafka between projects, and the data scientist can only just run code. So they can maybe upload jar files, run code, and read derived data, so data that's output from their jobs. Now, the really interesting thing about this from a Hadoop's perspective is that we're now delegating the administration of privileges to users. So we don't have a sysadmin here anymore. You as a user can add people to your project. If you own it, you can remove them, you can give them different roles. The admin is out of the loop here. So the next point is the quotas that I mentioned already. So if your project has a quota in the file system, that's pretty straightforward. But the YARN quota is an interesting one. So the YARN quota is basically saying you can set a particular number of minutes, CPU minutes, for each project. And when the minutes expire, you can decide what to do, either let the ongoing jobs complete or kill them. It's just a policy. And the interesting thing you can do with that at the moment is then, if you know the current load on the cluster, we can charge a bit more. So if the cluster load is very high, we want to disincentivize people from running jobs. So what we'll do is we'll make the price a bit higher, and if the cluster load is lower, they'll run them maybe at night time to take advantage of that. So you can share data sets between projects. This is just, it feels exactly like Dropbox. That's our idea there. The delegation of access control to the file system, it kind of looks like this internally. We have HDFS, we have projects, each project gets a subtree. If I have a data set D that's imported into project 1, it looks like it's there in your file system tree, but in fact, we don't even use symbolic linking. And the really interesting thing about this is the metadata point I was making at the beginning, which is that, well, what happens if I go to the file system and recursively delete this project? Well, the default implementation we have at the moment is it will delete everything. It will delete the users, the groups, and so on, and you'll have no orphan data there. So maintaining data integrity is more important for us than anything else at this point. Now, we had a question about Kafka. How do we delegate access control to Kafka? So in Kafka, from version 0.9, they've support for SSL TLS certificates. And your broker can be configured with a certificate. Again, it's signed by our common CA. And for each user, we generate an X509 certificate that has a name like this, project name __ user ID. So when you write a program, and if you write a program that's launched in like a Spark job or a Flink job, we support both Spark and Flink, by the way. When you launch it, what we do is we send as a private resource in YARN a copy of the private key. And the private key then gets stored locally and cleaned up when the job completes. And that private key is used by the client to talk to the broker. The client can be a producer or consumer. And then when it's received by the broker will extract this particular name from the principal name, and then it'll then look in the database for the ACLs. So we're storing the ACLs in the access control lists in the database, not in Zookeeper. I want to do a little demo, so I'm going to just jump through some of these things here. We support free text search for metadata. So if your data is in the database and it's your single source of truth, your metadata is there, how can we get it out? Well, the database that we're supporting has support for an event API, which streams all of the updates, and you can select tables you want to get the updates from. It's pretty much zero overhead, and we take that data and we pipe it into Elasticsearch. And we do it in a way that's highly available. So if our server that's doing this goes down, the data just accumulates in a table in the distributed database, and when the server starts up again, it empties the table and pushes it into Elasticsearch. And the delay we have on this is really about a second or two. We also have support in our front end for designing extended metadata and entering it for files. We support notebooks. We support Flink, Spark. We hope to support Apache Beam as well soon. But the notebook we're supporting is Zeppelin, and we have support for multi-tenancy. So if you're running Zeppelin within a project, somebody in another project won't have access to it. Now, one of the problems we had with Zeppelin the last year, if you've used it, is that if you have multiple users using Zeppelin on the same machine, the Spark context is created local on the machine, and you can pretty quickly overwhelm it. So in the last couple of weeks, we've added support for having the Spark context in YARN with help of the Livy server developed by Cloudera. All this is based on, the installation of all this is based on Chef. So we've Chefified everything. You can pull up a whole cluster on your laptop with Vagrant up. Well, there's a script around it a little bit. And if you want to deploy it distributed, we have a tool called Caramel. And Caramel will take a YAML definition of a cluster, and any chef cookbook you want to run, or any recipe you can put in there, and it will run them. This stuff is real. It's running in Sweden. We have a data center running up in Luleå beside Facebook. Facebook has a huge data center in northern Sweden in a place called Luleå. And we have 152 machines in the data center. We plan to scale to several thousand, hopefully. And Hops is running there. It's running there as a service for researchers in Sweden. We have about 60 users at the moment. It's still in closed beta, but we'll hope to open that up during the summer. So I'll give you a quick demo just to show you what it's like. Where it starts in. So this is, so this is the access control. So Zeppelin decided, because I'd logged out, it didn't want to be logged in anymore. Okay, so if I log in, I can see here, okay, so I've just logged in. We have support for free text search up here. We can see I've found a data set, so I can actually look at a data set, decide if I want to import it or not. We have support for projects here on the right-hand side. So you can see if you can see it there on the right-hand side, these are projects here. And you can create a new project by pressing that button. You can go into a project. On the left-hand side, we have Zeppelin. You have your notebooks here. We have jobs, Flink and Spark here. Kafka queues, and we have a Kafka schema registry as well. And then we have a dataset API. So you can see we can associate metadata by attaching it to these directories as well. If we look at our settings, you probably can't read that, but you can see the amount of CPU time you have left and the amount of quota you have left in HDFS. You can easily add members to your project. Just pick someone down there, and then we have this metadata designer. So we're in the process of designing new tools as well for this. If you can see that there, such as Uzi. Okay, so just to sum up then, so what we're talking about is a new platform called HopsWorks. It's a new distribution of Apache Hadoop. It has a distributed metadata backend, and what we've done at the front end is we've leveraged that metadata, distributed metadata, to build multi-tenant Hadoop as a service. And I think it's a world's first, so there's nobody else who does this. There's no other Elastic Hadoop out there. It's all open source. We're a research lab, research group. If you're a researcher and interested in doing something cool on HDFS or YARN, this is the platform for you. So just to give you an idea of the kind of things you can do in much quicker time, I had one master's student did erasure-coded replication for the file system. He did it in about 7 or 8 months. We had one who did the quota-based stuff, and you can think of any idea you want to do to extend the file system or YARN. You can do it a lot easier in this platform than in traditional Hadoop. So the other things we're trying to do is make it self-service. So we want to get the admin out of the loop, and we want to make the platform more managed by users than currently the case. And we're trying to make it tinker-friendly, so it's out there. So there's a lot of people who've been working on this. I'm just one of many, and mostly based in Sweden. And you can go visit us or like us on Twitter. Thank you.
So I guess we have time for 2 questions, and some of you can find your places.
Thank you very much for a great presentation. Very interesting. My question is in regards to quotas. Network quota is not less interesting when storage quota, both in HDFS and in YARN. So are you planning to introduce network bandwidth quota?
So, well, I guess this is more a question for the general YARN community. So are we interested in adding network quotas? Yes, of course. So as you know, cloud computing platforms like Amazon support network quotas and so on. At the moment, there's 2 main quotas, I guess, ways of sharing resources that are missing in YARN. One is network, as you mentioned, network bandwidth, and being able to allocate that to applications. I would say when Docker comes in as the main underlying execution engine in YARN, which it is in the process of doing, then that should hopefully, we should get some support for that. The other one is, of course, shared access to disk. So you have multiple containers running on the same physical host, and at the moment we still don't control access to or mediate access to disk. So you could have one container that's hammering the disks hard and the others, and there are 2 limitations, but they will be addressed eventually.
Any other questions? Well, thank you, Jim.
Okay, thanks.